Okay, the next talk is Entrysign, create your own x86 microcode for fun and profit by Matteo, Chris, Eduardo, and Josh from Google.
Hello, thank you for coming to our tech talk now. My name is Eduardo, and this is Matteo, Chris, and Josh. And we're going to talk to you about some research that we spent working on last year. And we're representing a larger group. Not everyone is here, but Tavis, who is someone that worked a lot on it as well, is not here. This is about Entrysign. Entrysign is a security vulnerability we disclosed a couple months ago. They will come back later. This vulnerability allowed us to write arbitrary microcode. And the first part of the presentation is going to be me explaining you more or less what is microcode, why it matters, things like that. Then Josh is going to spend a little bit of time explaining you how everything started, how we were able to read microcode, even though we didn't know what was going on. It involved staring at bits for a very long time. Then Chris and Matteo are going to tell you about the vulnerability and how we wrote microcode and decrypted them and so on. This vulnerability, it affects all Zen CPU microcode, which means that all CPUs, all AMD CPUs, you can write your own microcode, either because there is a vulnerability or because they didn't sign it before. Anyway, so in order to explain to you more or less what it is that we're going to be talking about today, you need to understand what is a very basic model of a CPU. And this is like a 20-year-old or more basic model of what a CPU is. And it's a three-stage pipeline. Modern CPUs have way more, but this is good enough for you to understand what it is that microcode is. First, the CPU fetches the instructions that it's supposed to execute. It fetches them from memory, so it gets a bunch of bytes. Then it decodes them into something that kind of makes sense. So for example, push something to the stack or flush something from some memory address and so on. Then it executes the instructions that it has there. And that last step, well, every step is written in Verilog in Silicon. But this last step, essentially, you can imagine it as a switch statement that just has a bunch of operations. And this is more or less how it looks like in a very simple arithmetic logic unit. Now, that kind of works for very simple CPUs, if you just have to do additions and subtractions and stuff. But x86 is more complicated than that. This is the first 2 pages of the list of instructions of x86. This is the first 6, and there's a lot more. And each one of those instructions is complicated. This is one of the most common instructions in x86. This is the return instruction. And you might think that return is just like push and stuff, but it's more complicated. And a lot of this is implemented in Silicon, but some of these instructions are the same again and again and again. So it doesn't make sense for CPU architects to just write the circuitry this way. So the way that this is implemented is that the complicated instructions are converted into simpler instructions. So some, like for example, move, is just essentially the same instruction. It's just a move is a load. But something more complicated, like an xlat, which is a lookup table, then that has at least 3 micro-ops. This is very simple, or high-level very simple. And this is an example of, this is an image of a die of a very old CPU. It's one of the first CPUs that implemented x86. And you can see in the bottom left corner is a microcode unit. And that is the thing that hard-codes what each instruction is supposed to be, more or less. We can zoom in a little bit. This is, again, a better quality picture. And if you zoom in a little bit more, you can still not figure it out. But someone spent the time to connect the dots and figure out what it means, which was a bunch of instructions like that, which is to zoom in, it looks like that. If you zoom in more, it looks something like that, which is microcode. This is the original x86 microcode from some guy called Reengine that spent a lot of time reversing it, which is very cool. Now, microcode, however, was only possible to be read. It was in a read-only memory, which means that if you had a mistake, you are doomed. So this was a problem one day in 90-something, where accidentally a bug in CPUs from Intel made so the divisions don't work. And it was in the front page of the New York Times, and it was affecting their business and so on. And this was the person that found the issue. He's a professor from somewhere. And the bottom left corner is the CEO of Intel at the time. And eventually, Intel had to do something that was a big deal at the time for them, which was they offered to replace every CPU, which is a big deal. So yeah, Intel will exchange any CPU for anyone that calls us. So I don't know. Maybe you can still call them today and find one in eBay or something like that. The year after that, Intel announced that now they can patch microcode. Now, patching microcode is complicated, but I'm going to explain to you more or less what happens. So this is a Zen CPU. This is an AMD CPU, but Intel CPUs also have similar behaviors. And this is a die shot, like the one I showed you before, but not as beautiful. This is the floor plan, so explaining you what each section does. And you have the MS-ROM. The MS-ROM is a microcode sequencing ROM, which is where like the microcode is stored. And this is a reverse engineered version of it, but this is a simpler version of that. Josh is going to explain you more into what's going on. Essentially, it just checks, is this address microcoded? Sorry, if this address in the RAM or not. If it's in the RAM, it's not a normal RAM. It's in a special part of the CPU that is fast to access. Then it goes to execute code from there. Otherwise, it reads it from the ROM. Very simple. Now, the way that you write things into this special version of in this part of the CPU is by being root. So you need to be root in order to be able to write this microcode RAM, which is not a big deal, I guess. So who cares if you can write microcode, if you need to be root as a starting point? And yeah, of course, when we published this, people on Hacker News were asking, oh, so who cares about it? And it's a good point. These three people care about it. The first person is a hacker, kind of. And there are three features of the CPU that don't trust the root. There's more than three, but this is three that I chose randomly. And I will explain a couple of them. The first one is the RTM. The RTM is a very simple, well, not simple. It's a tool that the CPUs use in order to assert trust on the boot process. And essentially, the way it works is that it kind of reboots. Not really reboots, but it reinitializes the core. You can see more or less what happens here if you're interested. But you reach a trusted state after you run this instruction. And after that, the TPM gives you some secrets. And this is the foundation for a couple of features like Windows Hello, Microsoft Intune, and System Guard. And so with this, you can, in theory, bypass all of this. There's another thing, which is confidential compute, which is for like when you don't trust your cloud provider, you can, in theory, think that you can just trust AMD. Good luck with that. And these are the only parts of the trust of the TCV, of the computing base that you have to trust. AMD, hardware, and firmware. Everything else is untrusted. Everything is red, is untrusted. And this is an important part because from the architecture of AMD, the microcode is part of the trust boundary. So if you can execute your microcode, you can break confidential compute. One other reason that is cool to do this stuff is that we have scientists. There is a research that was done when people were able to execute arbitrary microcode on the Atom, where they implemented a couple of stuff like constant time division, the pointer authentication, and other stuff. That is kind of cool. Conditional hardware breakpoints, who doesn't like that? And now you can do that in AMD if you want. And the difference is that with Atom, you need to buy a special cable, and I don't know, you need to launch fork. With AMD, it's just easy. You just like run our tools, and then you can just write arbitrary microcode. Another thing that is cool is that there is this Chinese company which for some reason thinks that they can run RISC-V on AMD Zen CPUs. We don't know how to do that, but they are offering you 20,000 RMB to do it. So it sounds hard, but good luck with that. And finally, reverse engineering. Reverse engineering is also very cool. These are the only two microcode updates that we know have been documented, or at least I know have been documented. One is from Intel, the other is from AMD, and they explain more or less what they do. But usually, microcode updates don't explain that much what they do. So if you want to do bin diffing or something like that, then it is a good, it will be like allowing you to read and write microcode is the way that you do that. So with that, my colleague Josh is going to tell you more.
Cool. Thanks. OK, so hopefully now you have a little bit more context of what microcode is and why you might want to patch it. And this is where we started the project, and we started wondering, like, would we even go about reverse engineering microcode? We didn't really think at all about trying to break the microcode updates. It was really just about reverse engineering to start with. And so we had like a bunch of different questions that we might want, we tried to answer here. So some things you might think of are like, I want to go find bugs in some instruction. So let's say already rand would be an interesting one. Unfortunately, we don't have enough information today where you could probably do that. We're missing the microcode ROM. We'll talk more about that. But maybe in the future you could do this. But things that we can do today are like maybe you want to go look for bugs and how AMD actually patched a CPU bug and see if they missed anything. So that's one thing we could go look at. And also maybe you want to, often the vendors will release microcode updates before the embargo is up because they're considered a black box. And we're going to show you how they really aren't, at least for AMD. And so we came up with this list, basically looking backwards now, of kind of 5 steps that we went through to actually do the reverse engineering. And then based on all that, you kind of study the results, and maybe you, if you're lucky, you can figure out what's going on. So we'll walk through these now. So the first step is to actually acquire the microcode updates. So we haven't really talked about like where they come from, but right, AMD and Intel, they author these. There are, I don't know, let's say a few hundred of these over the last few years. And they submit them in a couple different ways. The most kind of rich way to get all of these is to go through the BIOS updates. There's just more microcode patches that appear there. And so there's already an open source repo that basically crowdsources BIOS updates and asks people to extract their microcode from it and then submit here. And this is what we did. You can go there, you can download a few hundred microcode updates. And this is where we started. And we quickly realized that we had this assumption everything was encrypted. And I started looking through here and noticed that actually most of the AMD microcode updates had not been encrypted from like, I don't know, 2020 to 2022. And then like every now and then they were encrypted. It was really weird. It seemed like they had some bug in the process. And this was like a huge kind of revelation for us. And we kind of pivoted. Originally we were going to look at Intel and AMD, but at this point we just said, all right, let's figure out what we can figure out about AMD now that we have plain text microcode. So if you open up one of these binaries, they're basically just a binary blob, and you install them by essentially calling write MSR pointed to this binary blob. Matteo and Chris are going to talk more about the signature part and all the kind of issues there. But if we look at just the actual data that's being signed, there's basically 4 different areas here. We have some metadata that talks about like how the patch should be applied and some other information there. And then we have 3 patch contents. So the first one, basically, Eduardo mentioned like there's this hook and replace, right, where you say, I want to patch this ROM address and replace it with my patch. And that's what this first section is. The second section, these mask values, these are basically a way that we found where AMD can turn non-microcoded instructions into microcoded instructions. We'll talk about that a little bit more in a bit. But like essentially, very simple instructions are not microcoded by default. And this is actually like a pretty cool way to hook those. And then finally, we have the actual patch contents. And so the patches consist of these bundles called quads of 4 micro instructions. And these are a like kind of RISC-like language that we'll talk about here in a second. And then each of these quads is also paired with a sequence word, which basically instructs the microcode engine what to do next. And you'll see more about that. So next, we need to understand kind of how the microcode interacts with the rest of the system here. So this is a more kind of detailed view of kind of what Eduardo showed before. This is a detailed but also simplified view of kind of the Zen CPU architecture. And the critical piece here is basically where you get to the point where it's decoding the instruction, like it just fetched the x86 bytes. Then it decides, is this a fast path instruction? So these are the simple instructions that just are a couple micro-ops and it's kind of a fixed list of micro-ops. Or is it a microcoded instruction, something like return or already ran? And that ends up going into this gray box that's the microcode engine. So if we zoom into that engine, you can see now in more detail, for the case where we have the microcoded instructions, there's some circuitry in here that says basically for every x86 instruction that's microcoded, like you need to start executing at this specific ROM address in the microcode ROM, right? So like already ran, maybe it starts at like hex 400. And that's the first piece. And then basically there's a cycle here where it goes into the ROM and it runs some, kind of runs in quotation marks here, some instruction bundles. These get pushed out as micro ops to the back end, which is kind of this bottom piece here, which is where they actually turn into executed operations. And then it goes back to the sequencer, and then it continues the cycle until it basically breaks out. And then alternatively, you can go down below this for the fast path instructions. And this is the same view now that it's been patched, right? So we take that blob from AMD, we install it, and these yellow boxes now appear and have the contents from that patch. And this is where at the top we have the match registers, which say like hook this ROM address. So this address selector checks that on every single PC. And also there's this patch RAM, and this is internal SRAM. It's not. It's completely separate from what the x86 instructions have access to. And so basically it jumps to a corresponding patch RAM address if there's a match register that matches. And then similarly for FastPath, there's another way that you can hook those as well and then jump into the microcode. So the next step, now that we kind of understand how the patch gets applied and what it does, we really have no idea about the microcode instruction set. So this is not x86. It's basically a RISC-like language, and there's very little documentation on this, so this was pretty challenging. The history here is that AMD back in like the mid-90s bought a company called NextGen, which was making an x86 clone, and for that clone they were using a thing they called RISC-86 to implement the x86 instructions. And AMD bought them. This turned into the K6 from AMD, and that's basically kind of what is still used today. The kind of ideas are the same, but a lot of the details have changed, over the last 20 years, or 30 years at this point almost. So there's two pieces here, right? Like, we need to understand what the instruction set is, like not only what are the opcodes, but like where are the fields and like which bits actually correspond to those. And then also, how does control flow work, right? Like, how do we kind of know how we get into and out of microcode, but we have no idea yet about how branching works. So to start with, like we had no, like we didn't have Entrysign, so we just had a bunch of bits, and we can't change them because the signature won't match. And so I kind of like pretended to be a data scientist, and we basically just stared at bits for a long time. And so here we have like one example where I was doing some bitwise correlation, and you can see there are like relationships that show up here. I still couldn't really tell you exactly what they mean, but it at least gives you some idea of like where things might be segmented. And we've overlaid here, kind of at the top and bottom. You can't really see it in detail, but that's like our current understanding of like an XOR instruction. And you can see like the immediates and some of the other things do correspond to where these, relationships were. And this is all we had for like months. And we kind of just stalled out here. We kind of figured out some stuff, but not a lot. Today we'll talk about Entrysign, but we basically have the ability to install arbitrary microcode. And so, of course, now we can just flip bits in the microcode and see what the actual corresponding like x86 effects are at an architectural level. There's a tool in XenTool if you want to look at this. XenTool, by the way, is the thing, like the code that we published on GitHub, so feel free to look at that. And here's like some examples. Basically, there's like a top-level class code that then changes how the rest of the instruction is formatted, and these are like 3 examples of what that looks like. The other half of the instruction set is the control flow, and this is like somewhat complicated, I guess, and more different than how x86 works. So there's like kind of 3 aspects that control or impact the control flow. So right here we have like an example flow where we come out of the ROM, we go into some patch instructions, and we jump back into the ROM. So first we have these sequence words, and you can think of these are 32 bits. They're attached to every quad, and they're basically like an instruction for the microcode sequencer, which is typically some kind of jump, right? So we have some jumps to different patch RAMs and then jumps to ROM. It can also say like basically stop executing microcode and then go to the next x86 instruction. One thing that makes this more complicated is the architecture uses branch delay slots, which essentially means that all of these sequence words don't actually apply until the next quad finishes, which mostly makes it harder for us to reverse engineer this. We have to like kind of keep track of what the previous delay slot was, and especially when you have like conditional branches and things, it gets a little complicated. And then finally, the actual micro ops themselves can jump, right? Like we can have some kind of J and Z or something similar to what you're used to in x86. Okay, so the last piece that we're missing here is actually which x86 instructions correspond to which microcode ROM addresses, right? So we need to figure out like where is RDRAND. If we want to back to RDRAND, we need to know like which address that we want to hook. And this also, we couldn't do this until we had Entrysign. And there was some previous research, like Eduardo mentioned, there's been some research on old Intel and very old AMD CPUs, and we basically reproduced that. The idea is that you're going to sweep over all the different possible ROM addresses and build a patch that sets a canary value, something like RAX equals 1337, and then you install that patch, you sign and install it, and then you go over every single x86 instruction with some instrumentation and see, do we see that canary value? And if so, you know that there's some relationship, right, with that ROM address and that x86 instruction. Again, we have kind of examples of how we did this, and we have some example output. And this is how, when you use Zentool, it knows like where RDRAM lives. So putting everything together, we do know quite a bit, but there's still a lot we don't know. So that's kind of the caveat here. We can, and you'll see here in a second, we can kind of analyze some patches, but we still don't know the vast majority of like instructions. And the biggest thing that we're missing is the microcode ROM. As far as we know, there's no way to read the ROM from the microcode itself. And this is something where you probably would have to like image it with a scanning electron microscope or something similar. Okay, so we have a couple of examples here of what these patches look like. So this is ret bleed, which is a vulnerability from a couple of years ago. And the patch, the idea here is this is like the patches are cumulative, right? So this is a lot of patches all combined into one. You can do something like bindiff and just zoom into one, like what changed since the previous patch. And so in this case, this is the very first time we understood anything. This was before we had Entrysign, and we were just staring at bits. And Eduardo mentioned this is the one time really where AMD ever mentioned anything in documentation about what a microcode patch does. And they said basically that it sets a bit on a specific MSR. And so we stared at this patch, and there's basically 3 micro-ops that you see here, followed by a no-op, because there always has to be 4. And then it jumps back to ROM. And if you look at this a little bit more, you'll see it's basically reading out of memory. This is like internal microcode memory, ORing in that bit, and then writing the result back out to the memory. So our assumption is that this MSR is implemented at this like internal microcode memory. Alternatively, the Zenbleed bug, so this was also a recent AMD bug, is quite a bit more complicated in the patch. So this was a instruction, it was a bug in the v0 upper instruction, and it wasn't a microcoded instruction to start with, so they're like hooking that, and then they have to replace all the original exception handling that was in the like hard-coded instruction in microcode, and so you see all these conditionals now. And then finally, they check if you're in AVX mode or not, and then they actually do the v0 upper at the very bottom. All right, so hopefully now that you understand a little bit more about what the microcode looks like for AMD, Matteo and Chris are going to talk about how we broke everything.
Sounds good. Now that Josh has already told you about something about the format of the microops itself, let's take a look about the container format. So if you take a look at one of these microcode updates that you can get on GitHub, you see that there's some structure. So first there's a 32-byte header, which is more or less documented. Then there are some blocks of what looks like random data, and then finally there's the payload. So we know that these updates are signed and sometimes even encrypted. And so we can try to do some tests on these blocks. So first of all, one thing that we see on the blue block, the first one is that it's not only random, but also it changes in every update, and it's 256 bytes. And then the other two, they're also random and 256 bytes, but they stay the same all the time. And if we modify any of these random blocks as well as the signed data, we know that the CPU stops loading the update. It will like throw an exception when you try to load it. So we can try to make some hypotheses about what these fields are, and one thing we could say is that the blue block could be a signature because it changes every time, and that makes sense because the signed data changes, so the signature also changes, whereas the other two could be some public key or some other data that the CPU needs. And we know that the orange block and the green block are different because there's also a timing difference when we modify the data and try to make the CPU load it. So we know that they're like not the same thing, even though they both stay the same. So now that we think that this is a signature, and there are kind of like 3 popular choices that people use for cryptographic signatures. Like one of them is using a Mac, like HMAC. And this doesn't seem like a good fit because Macs are usually on like much smaller than 256 bytes, and also because if AMD really had used a Mac, they would have had to include the key that you can use to make new Macs inside the CPU, which would be like insecure because then you could just get it out and sign on an update. So it's not likely that. Other thing that people like is to use elliptic curves, such as ECDSA or EDDSA. Again, these signatures are much smaller than 256 bytes, so this is likely not it. And the third option is RSA. RSA seems like the best fit here because the signatures are bigger, like 256 or even more bytes. And then so the public key is the same size as the signature, which is what we see here. So this looks like a good candidate. And so we would like to see if this is really an RSA signature. And one way we could do that is to exploit the structure that is usually present in RSA signatures. So RSA signatures, like the signed data is not random, and it has some kind of distinguishable structure. And people have come up with a bunch of standards to how to make these RSA signatures. And one popular one, which is also very simple, which what what we show here is called PKCS number 1. So in this standard, the hash of the signed data is prefixed with some padding that has a pretty specific structure. In this case, it's like 1 solo by FFFF and then by null byte. And we can basically try to see if AMD is using RSA with this padding scheme by raising the signature to the power of E, which is the public exponent, and doing modulo the modulus, and seeing if the result has exactly this structure. And if it is, then we know that we are correct. And one problem is that we don't know what E value AMD is using. In theory, they could take any value, but in practice, we know that people tend to use a few specific values, like 3, 17, and 65,537, because they make the computation more efficient. So we can try to test. So let's first try with 3, and we get something random, so that's probably not it. And same with 17. However, once we try to do this with the 55,037, then we see that this has exactly the structure that we showed before, so we are pretty sure now that this is an RSA signature. And if we look at this, one thing that kind of stands out is the hash. And the problem with the hash is that it's only 16 bytes long. And normally, when people make cryptographic signatures, they want to have at least 128 bits of securities these days, which means that the hash would have to be 32 bytes long, not 16. And the only kind of hashes that have a 16-byte long digest are MD5 or the other kind of weird, like maybe a bit broken hashes. And so like when I saw this, I remember thinking, hey, like, this slide looks a bit broken. Like, are we sure that they're really doing this properly? Maybe we should take a closer look and try to see if it's broken. So unfortunately, at this point, we kind of hit a roadblock because we couldn't figure out what this hash was. Like, we tried to hash the data, the signed data, and the only thing we could see is that it's on MD5, it's not SHA-2, it's not like basically any well-known hash function. And we couldn't figure out what it was, and we got stuck. So now Chris is going to tell you how we got unstuck at that point.
Right. Let me tell you how we traced the microcode update routine with IBS, the CPU feature from AMD. We were measuring the microcode update procedure's latency when flipping bits in different positions in the update file using RDTSC in this example. While doing this, we also experimented with another feature called IBS, instruction-based sampling. It's an AMD CPU feature meant for performance measurements. There's a very interesting blog post linked here. It has some more in-depth details about this thing. How this feature works. It's based around an instruction counter of executed microcode instructions and a configurable maximum. When this maximum is reached, then the counter is reset to 0, and some information about the previously executed microcode instruction is put into an internal buffer, where it can later then be retrieved by the user. The information that you get in this internal buffer is, on one side, it's the type of memory access, if there's a memory access. It's the size of the memory access, the virtual address where memory was accessed, and the physical address. If there's no memory access, then we don't get much additional information, just that it's an ALU instruction. How is this feature configured? It's based on mainly 2 subfields in the IBS op control MSR, or model-specific register. One contains the current counter, and the other contains the configured maximum. Normally, you would configure this in a sampling mode, where you say, for example, to sample 1 instruction in 1 million microcode instructions. But we found that you can also target 1 specific microcode instruction. So in this example, we, for example, target the 100th microcode instruction after you activate this feature. And if you do this repeatedly, you can get a trace of all the microcode instructions that are executed while x86 instructions are executed. In this example, there's always a 1-to-1 mapping between x86 instruction and microcode instruction, but there can also be x86 instructions that use more microcode instructions. If you do this on the microcode update routine, then you get a lot of, a very long trace, and this is an excerpt from this. In total, there are over 1 million microcode instructions in the trace of the microcode update routine. The information per instruction is not a lot. You only get the memory information, the memory address information. But in all of them together really tell a story of how this function is implemented. Let me now tell you how we use this to identify the mystery hash. Let's look at the microcode update file format again. We have the RSA signature, the public key, some additional data that's not relevant right now, and the signed data. If we modify the signature or the signed data, then, as you would expect, the update does not apply anymore, it fails. That makes sense, the signature is not valid, so yeah, it's rejected. But if you modify the public key, it's also rejected. Why is that, and why is it even here? Normally you would expect it not to be there. So it turns out that this is typical in the embedded world. Instead of storing the whole public key, which is quite big, you just store a hash of the public key. And yeah, now let's look at this hash in detail. When you create an IBS trace of the microcode update routine for a microcode update where the RSA public key is modified, then shortly before the end of the trace, you will find something like this. And here you can identify 16 rounds of some algorithm that looks, it's like all these rounds are basically identical. Only the last one is slightly modified. Let's look into one of them exactly. So here we can see in red the RSA public key is accessed, always 16 bytes and always sequential. Then later we see there are 11 constants used, also 16 byte. For the last round, there's an additional 12th constant that is used before the round is executed. Now, let's summarize what we know about this algorithm, this mystery hash. We know it's 16 bytes word-based. It uses 11 constants per input block, and there's one extra constant used in the last round. This matches perfectly with this algorithm called AES-CMAC. It's based on AES 128, so it uses 16-byte words. And the 11 constants are just the AES key and 10 round keys generated from the AES key. In AES-CMAC, we also have an extra constant that's used in the last round. That's called K1 in the diagram here. So this is a perfect fit, and it turned out to also be the exact algorithm that's used by AMD. And Matteo will tell you more about AES-CMAC.
Great. So now we think we have identified the mystery hash function. Let's take a look a bit more closely. So if you sketch out the data flow of CMAC, it will look something like this. You first have to split your data into 16-byte blocks, and then you run each of the blocks through a function called C, the compression function, starting with the IV of 0, and then the output of the compression function is fed into the input for the next round. And then the hash is simply the output of the last compression function. And in this case, so we know the K1 as well as the AES key that is used inside the compression function, as you see on the bottom left, are hard-coded and fixed. So this is it's all the same in every CPU. Now, you look at this and you see that this is like standardized by NIST and is supposed to be a secure MAC, and so you think this might be all good. If this is AES, it's like, secure cipher, but there's actually a small problem with this, which is that CMAC is a MAC, it's not a hash function. And it's not designed to be a hash function, it's actually not a secure hash function, it can be broken. Now, there's a small asterisk there, which is that in order to break CMAC when used as a hash function like here, you actually need to know the AES key. But luckily for us, AMD put this key inside every single CPU that they ever made, so we can probably get it out somewhere. So let's just assume that we have this key now. How can we actually break this hash function? Well, it's pretty easy. Suppose that you have your block, your data, we split it into n blocks, and then you have a target hash, and you want your data to have that hash on the CMAC. So you first run the CMAC algorithm forwards on your data blocks like normal. And then for the second part, you run backwards from the target hash. So you have to construct the C-1, which is like kind of the inverse of the compression function. You run it backwards, and then this will produce a garbage block. And the way that it works is that if you hash your data followed by this garbage block, the hash of that thing is equal to the target hash. And this works for any target hash and any data, as long as you can accept that there's like one 16-byte block of garbage in your final data. And this C-1 function is pretty easy to construct. So this is the compression function forward. The input is the state as the old and the data, and the output is a new state. And the inverse is like very easy to construct. As long as you know the key, you simply decrypt the new state, and then you XOR the old state on top of the output, and then out comes the garbage block. So it's pretty easy to make. So let's now try to get this AES key. So as we saw before in the AES trace, this key is just somewhere in memory. This is like just a regular memory address. And so like the first thing we thought about is, well, can we just like read it out? And well, unfortunately, it seems like AMD thought of this, because if we just try to map this address somewhere in the kernel and read from that, the CPU just gives you a page fault. And yeah, if you try to read this from non-page mode, then it just returns hexFF, so that also doesn't work. And we can also not read the memory speculatively, and because write MSR instruction, which we use to load microcode updates, is serializing, so you cannot like speculatively execute it. So we thought, okay, well, there's some memory, it's there, it's in RAM, and we cannot read it from the CPU, maybe we can use something else. And so like the thing we thought about is like we can try to read it from the PSP. The PSP is like super privileged in AMD CPUs, it has access to everything, and so maybe it also has access to this memory even though the CPU doesn't.
Yeah, I will tell you how we got full physical memory access via the PSP. So what's the PSP? The PSP is an ARM microcontroller that's embedded on modern AMD CPUs. It has full access to the system RAM and other resources of the system. It's responsible for booting the CPU before even the BIOS is activated. After boot, the PSP offers a couple of additional services to the x86 core. In 2018, a company called CTS Labs found a couple of vulnerabilities in AMD Zen 1 PSPs. One of them is called master key. It's very interesting to us because it allows code execution on the PSP. It's a signature validation vulnerability. How does a PSP boot? It has an embedded on-chip bootloader that is responsible for loading further firmware from the SPI flash that's embedded on the motherboard, where also the BIOS is stored. This firmware is organized using a directory. This directory is not signed. It contains a list of modules, of firmware, PSP firmware modules that the PSP might be interested in loading. It includes the location of the module in the SPI flash and some identifier of it. The modules are individually signed. The PSP directory is not signed. There are different types of modules. There are code modules that are fully signed, as you would expect, but there are also configuration data modules that are only partially signed. In this case, only the header is signed. What does the header contain? The header contains some fields, for example, the size of the module, if compression is used or not. What's important is it does not contain information about what type of module this is or what the identifier is. That's only in the directory. We can use this. We can combine an existing code module that is fully signed, use the body of that module, and take the header of a configuration data module. And now we have a new module that is where the body is modifiable. The whole module is still valid, the signature is still valid, and we can embed some new service. In this case, we embedded a memcopy service that was able to copy physical memory. Now, let's see what we have now. We have full physical memory access. We can copy memory around, but this only works on Zen 1 CPUs with very old firmware versions. It still was very helpful to us because, yeah, we want this key. And now let's look at how we got the key using this. So the first thing that you would do is you just read the key from where you expect it to be. But this didn't work. There was only zeros there. We don't know exactly why, but it just didn't work. But what we found close to this area is something called the CC6 safe area for one of the CPU cores. This CC6 safe area is a place for the CPU to store its internal data while it is partially shut down. To save power, it goes into a sleep state called the CC6 sleep state, where all internal SRAM and so on is turned off. And to recover from this, it has to store, for example, the register values somewhere. It stores these in the DRAM, and yeah, this is called the CC6 safe area. What we also found that is stored in this area is the currently active microcode update. You can find the fields again that Josh was talking about earlier, like the mask register, the instruction bundles, and so on. And we also found that you can modify these. They are not validated in any way. So this really gave us microcode code execution already. Only on Zen 1 though. So what's the plan? It's, we can power down one of the CPU cores, then override the microcode patch in this core, and then power it up again. And now we have a core running with our own microcode patch. Also, from the reverse engineering in the beginning that Josh talked about, we knew how load instructions look in microcode, and we also know that these appear in IBS traces, including the addresses. So we combined this and took two load instructions, where the first one was loading data from the address where the key was stored, and the second load instruction would take that data as address, and it would leak in the IBS trace. And this really worked. We can see here how the first two iterations of leaking the first 32 bits and the second 32 bits looked like in the IBS trace. So when we did this, we found out that this is just the example key from the ASC MacRC. If we would have used that or known that earlier, that would have saved a lot of time. It's used from Zen 1 to Zen 4. In Zen 5, AMD changed the key, but we also found a way to extract that as well. Using a different method, we had direct physical access to the DRAM to do this. And now Matteo will talk more about how to,
Right, so now that we got the AES key, let's go down to reading and writing some microcode. Well, how do you forge the signature? How do you load your own microcode update? It's pretty easy. You make an RSA key that collides with AMD's own RSA key with the method we discussed it before, and you also make sure that this key is easy to factor so that you can factor it and use it to make signatures. This is very easy. You just brute force, and like within a few seconds you have a suitable key. Even if it has more than two factors, it's still fine because the mathematics still work the same, even though it's not how you're supposed to do it in RSA. And then you just like sign your update with this key, you put your key in the update, and the CPU will just like, oh yeah, this is like totally AMD's key, and accept the update, and then yeah, profit. We made a tool called Zen Tool that automates all of this for you so that you don't have to do it yourself. It's available in our GitHub repo, and it does a lot of things, like you can manipulate the header of the microcode, it can sign updates, it can print the contents. It even includes a rather basic assembler and disassembler, so you can like also take a look at AMD's updates and try to figure out what they do. So now let's show you how this works in practice. We have a small POC of us loading a microcode update that makes rd return 4 using Zen Tool. So what I'm about to show will work on every generation of AMD CPUs, but the constants might be slightly different, so you may have to make some adjustments, and this is on Zen 1. So first we check what microcode version this is running by just asking the kernel. And we see that this is running microcode version 8.0.0.1129, which is an official microcode update from AMD. We can find that in the GitHub repo that Josh mentioned that contains all the microcode updates, and use that as a basis for our backdoor patch. So we have a copy of this update here. We can print its contents with Zen Tool and see that that it's really the same version. And as you can see, the version is the same, so it's really the same update. We can also see we have a program that tests RD-run to make sure that it doesn't return the same output more than twice, that the output really is random. So in order to show you that for now RD-run is working as expected, we just run this test. And as you can see, it returns data that looks random, so that's all good. Now, let's create a backdoor patch that makes rd-run return 4, and we use the current patch that is currently loaded as a starting point. So we will put the code in the backdoor, and we will just use unused match register and two unused opcodes to hide our backdoor. The reason why we need all of these instructions is that we need to set the carry flag in order to make it look like rd-run succeeded. So we first set the register reg4 to -1, and then add 5 so that the final value is 4, and the addition overflows so that this also sets the carry flag. Reg4 is just an alias for the current operand of the instruction, so it always works no matter what the register rd-run is actually using. And also we set the sequence word so that this terminates the instruction right after, so that we don't crash the CPU, which can happen very often if you're not careful. So we now try to load this update, and if it fails, well, because we modify the update without actually updating the signature, so the CPU rejects it, and you can see even Zen Tool tells you that you might want to resign the update because the signature might be wrong, so we can do just that. We first check that it's really wrong with Zen Tool verify, and we see now that it's a bad signature. And yeah, there's a resign command that will generate a key that collides with AMD's key and then sign update with that key. So we run that, we resign our update, and then if we now try to load the update again, this time it should succeed. So we do this again, and this time like it succeeded, and we have also incremented the microcode version so that we see that it's our update. So now let's try to run the rd-run test again, this time on CPU zeros, because that's where we loaded the update, and this time it will return 4 twice. And if you run it again, you see that this returns 4 again. So it means this always returns 4. Right, so now we can write microcode updates. What about reading them? Well, so one thing that was mentioned before is that many of the updates are encrypted, and we see that as a trend. In Zen and Zen Plus, there were basically no encrypted updates. Zen 2, some of them are encrypted. Zen 3, Zen 4, Zen 5, most of them are encrypted, and basically Zen 4 and Zen 5, all of them are encrypted. And this is kind of bad for us, for our reverse engineering, because it means that we don't have any visibility whatsoever into the patches for later generations. So the first thing that we did once we got this to work was, okay, let's figure out how the patches are encrypted and decrypt them so that we can look at what's inside. So let's take a look at the IBS trace again, this time at the section where the microcode update is decrypted. We know that this is where it happens because this is the first time where the encrypted data is accessed when loading an encrypted patch. So we see that this time it's not load 16, it's load 4 and store 4, so it's like something different. It's definitely not AS, but maybe it could be some other well-known cipher. So what we did is that we identified the part where the decryption starts and then try to dump the values from all the registers to see if they contain some interesting constant that would give us any clue as to what algorithm this is. So we did the same thing as we did before. We replaced the first instruction using a microcode patch with something that just loads from the register so that its value appears in the IBS trace. And then like after a while, we tried all the registers, we got this constant. I mean, that looks interesting, right? It looks kind of random, so we basically just tried to search for this on the internet, and we get some results. Like most of them are relative to some like hash functions, but so it doesn't look related, but then there's one about this thing called the tiny encryption algorithm. So tiny encryption algorithm are like this, well, an encryption algorithm that, as the name says, is tiny, which means that the code is really small. And it would make sense that AMD uses something like this because they are constrained by the space in the microcode ROM, so it would try to pick an algorithm that takes the least space possible. And there's some variants like XT and XXT, and if we look at XXT in particular, we see that this is like a pretty good match for what we see in the trace. So first of all, it is using our constant, but then also if we look at this code side by side with the IBS trace, we see that the loads and stores match pretty much perfectly. So we are pretty sure that this is it. So the key for XXT is just 4 uint32s, so we can also try to extract that from the registers or the memory in the exact same way that we showed before. And once we did, we saw that we successfully decrypt the update, so that we know that this was really what AMD is using, but to our surprise, this still worked on Zen 5. So AMD changed the RSA key for signing on Zen 5, changed the CMAC key, did not change the encryption key. We don't know why, but I don't know. they did that. So this is good for us because we can also decrypt Zen 5 updates using this key. And finally, let's briefly take a look at how AMD fixed it. Well, if you look at the website, at the advisory for this, they tell you install a microcode update. And you may think, well, this doesn't sound like a very good idea because if they fix it in microcode, then somebody who has already loaded a malicious microcode patch could simply make like the microcode update routine do nothing, and then you would think that you have the update, but you don't. So, well, our understanding is that either the BIOS or the PSP is loading this fix patch at boot. We didn't really look into too much into that part, but we did look at like the contents of this fix in the microcode update. So what we found is that AMD essentially replaced CMAC with something more traditional called the Merkle-Dunbar construction. This is the same way that other hash functions like MD5, SHA-1, and SHA-2 are built, and it looks really, really similar to CMAC if you remember like the slide with the CMAC structure. The only difference is that now there's like this length block with another round of the compression function, but it basically looks the same. And the big difference is that they also changed the compression function. So the problem was that CMAC's compression function is kind of insecure because you can invert it. They replaced it instead with something called Matthias Meyer-Oseas, which is a standardized way of building a secure compression function using a block cipher such as AS. The difference is that this time, instead of having the same key every time, the previous state becomes the key for the next round. So yeah, we know that this is secure now, so this is fine. And it doesn't need to have a secret key in the CPU to be secure. So that's it. Thanks for attending our talk. And we hope you'll have some questions.
Great. Thank you so much for the talk. Are there any questions? No questions?
Hello.
Hello.
Just a question. You say you can read the encryption key from the RAM, right? From the dynamic memory RAM. Can you use the technique like freeze the RAM and insert it in another computer and read it? It was a very old technique to read physical memory.
Oh, you mean like cold boot attacks?
Yeah, exactly.
Yeah, I guess that would work. Should probably, yeah. We haven't tried, but we think that should work, yeah.
It works. It works. Every time it works. Every time I try, so it's very easy to do. Maybe next time. Thank you.
Hey, here on the right. Thank you for the great talk. So I'm not sure I understood correctly. So you couldn't read the key from the memory, right? But then when the CPU shutdowns, it saves the state, and then you can override the updated instruction for the microcode, right?
That's correct.
So this is what you can do from like a Linux kernel perspective, or from some different place?
You mean like reading and writing to the 66 area?
Yeah.
So no, you cannot write to the 66 area from the kernel, because like the CPU basically has a check that so if any software tries to write to that area, it will reject the write. It will like basically give you a page fault. So instead, we had to do it from the PSP, and it works when you do it from a PSP because the PSP is like super privileged and it has access to everything.
Okay, thank you.
Hello. I have a couple of questions. The first one was when you do this, like you power down and then you extract the state from that CC6 area. Is that like a race condition? Like you initiate the update and then from another core you put it in a power down state, or what triggers the power down if it is already running the instruction of updating?
Oh no, so you don't need to power down the CPU while it's doing the microcode update. You just like can power it down at any time, and you do this by simply like telling the OS, please offline the CPU. Like the Linux, you just like kernel, please offline the CPU powers down, and then there is always a microcode update that is loaded because usually the BIOS loads it, and so that gets written to memory.
It's not in the process of updating microcode. It is the last microcode update.
Yes, it's the last update that was loaded. Yes.
And the other question, so does I don't know if you ran this experiment on a physical machine or on a guest VM, but do existing hypervisors intercept this WR/MSR instruction and stop you from kind of overwriting microcode, even legit microcode?
I haven't checked, but I think they do, because I don't think it would really make sense for a VM to update the microcode, which would also have an effect on all of the other VMs that are running on that host.
But then the WR/MSR can be ran from user space, or is it only kernel space?
No, only kernel.
Then what is the attack surface? What is the threat model there? If someone who wants to overwrite microcode or patch it already has access to the kernel.
Yeah, the beginning of the presentation explained this more or less, but there are a couple features that assume that root is not trusted. One of them is the RTM, which is used by Windows Hello and Intune and SystemGuard, and the other one is confidential compute, and also SMM and BIOS and things like that.
Okay.
Yeah, confidential compute is kind of the big one because like the whole threat model is that you want to run your code on some public clouds like GCP, and you don't trust the cloud provider. So the hypervisor isn't trusted, but somehow like the CPU is still protecting your VM from the hypervisor. But of course, if the hypervisor can load malicious microcode, then this whole is invalid.
So you implicitly trust the CPU manufacturer in that case?
Yeah.
Okay. Thank you.
I've got one question about IBS specifically. What are the performance while you're running an IBS trace? What does the CPU do? How long does that take? Is it like a big performance hit while that trace is happening?
I didn't measure timing differences with and without IBS, but we were like creating these 1 million entry traces, and each of the entries we repeated like 10 times. So like we were running a couple of million times the update routine. It took maybe an hour or so maximum. So I don't know. I don't think it's a huge impact. It's probably not good to run it in production all the time, but yeah.
I mean, it's supposed to be a performance feature, right? So it's supposed to be for sampling and measuring what instructions are taking time and things like that. It's so in theory, it's not. And the only thing the CPU has to do is when an instruction retires, it keeps some metadata about the instruction that just retired, and then just keeps it around for a little while until someone reads it. And then it triggers an interrupt at some point. So it's not supposed to be super, super slow.
Right, yeah. Yep. Thank you.
So my question comes down to, I know that one of the things that you were doing is, just applying random microcode updates and seeing how instructions change or how behavior changes. When you're screwing with stuff at that sort of level, did you ever encounter cases where you're just creating broad system instability, where like your kernel just starts crashing or you stop booting?
Oh yes.
So like, how do you recover from that state where
you reboot?
Okay, you reboot. Okay, because this actually refreshes the microcode updates back to what?
Yeah. So to expand on that answer, when you reboot, the microcode update that is installed is gone. So we haven't yet managed to permanently break a machine with this, although we suspect that it must be possible somehow. If you try to run your own microcode, you will very quickly start to crash the machine. I think that this is in my experience. Either like you make an infinite loop, or it will just if the CPU encounters like a malformed micro-op, then it will just crash.
There were some types when we rebooted the machine, it didn't boot up again. But then doing a full power cycle where like all of the capacitors went down and stuff, then it did come back up again. When we started doing this research, people told us that we were going to break the machine, and we didn't manage to do it yet. But in theory, it is possible, right? Like we might accidentally write into something in the BIOS or something like that then makes it hard to recover. But in theory, who knows? I mean, the CPU people are the people from Intel and AMD are the ones that told us that this was not a good idea. They also told us not to brute force MSRs, and that was going to break the CPU, and that didn't do it either, so who knows?
Thank you.